Let us start. The first property is the linearity property. I have already explained that linearity property. Second property is time shifting property. Let's say if we have a signal xt and x of j omega is the spectrum of that signal, I denote it by this. This means xt and x of j omega, they form a Fourier transform pair. X of j omega is the Fourier transform of xt, or xt is the inverse Fourier transform of x of j omega. So I'll be using this notation. They form a Fourier transform pair. And this is, okay, like I'm writing it here, 1 upon 2 pi integral minus infinity to infinity x of j omega e to the power j omega t d omega. Okay. So now let us discuss the time shifting property. If we are shifting the signal in the time domain, okay, let's say its spectrum is x1 j omega. How is it related with x of j omega? It is straightforward. You replace t with t minus t naught in this equation. You will get x t minus t naught, that is 1 upon 2 pi integral minus infinity to infinity x of j omega e to the power j omega t minus t naught d omega. And this can be written as x of j omega into e to the power minus j omega t naught into e to the power j omega t d omega. Okay, now tell me, what is x1 j omega? What is the meaning of this?
X of
Can we say that x t minus t naught is the inverse Fourier transform of x of j omega into e to the power minus j omega t naught? This is the inverse Fourier integral. So the meaning is x of t minus t naught, that is the inverse Fourier transform of this term. Okay, this function. So we can say that x of, if xt, Fourier transform of xt is x of j omega, then the Fourier transform of delayed version of xt, that is x of j omega into e to the power minus j omega, minus j omega t naught. Okay. Now, can you tell me what is the relation between the magnitude spectrum and phase spectrum of x1, x and x1? What is the magnitude spectrum of?
magnitude will be same.
Is it same as the magnitude spectrum will be the same? Okay. And what about the phase? What is the relation? We can write from here, from this. This is, can we write it as phase of x of j omega, then what?
minus omega t naught.
Minus omega t naught. So this is the relation between the phase. There is only a phase shift. And you can visualize that also. If we are expressing a signal as a linear combination of sinusoidal signals, if you delay the signals, the corresponding, there will be a delay in the corresponding sinusoidal signals also. So, and we have seen that the delay in the case of a sinusoidal signal, that is a phase shift. That's why there is a phase shift. The magnitude will remain the same. Okay. So that is the time shifting property. And there is a dual of this property. I am just stating that result without proving that. The dual is xt into, if you multiply here, you are delaying the signal in the time domain. There is a multiplication by a complex exponential in the frequency domain. The dual is, if you are multiplying a signal with a complex exponential omega naught t in the time domain, its Fourier transform is, there is a shift in the frequency domain. Okay. And remember, when I write x of j omega minus omega naught, we sketch this as, this is x of j omega. We sketch it as a function of omega. And what is meaning of this omega minus omega naught? We are shifting that function. For example, if x of j omega is something like this, what is x of j omega minus, let's say, pi? Is it a shifted version of this? Is it something like this? It is shift by a factor of pi. Okay, so that is the time shifting property. Okay, next property is if xt Fourier transform is okay, so I'm writing it here xt sorry, there is a scaling factor 1 by 2 pi e raised to j omega t d omega. So what about x star t? It's conjugate. Can you tell me this from this integral you can get this property? If you take complex conjugate on both sides, what is that expression? X star t is what? 1 upon 2 pi integral minus infinity to infinity x star j omega e to the power minus j omega t d omega, isn't it? Taking conjugate on both sides. Now we can write this as, is it in the form of some inverse Fourier integral? We have to convert this into in the form of inverse Fourier integral. Inverse Fourier integral means this must be what? This must be e to the power j omega t. So we can write this as 1 upon 2 pi integral minus infinity to infinity x star minus j omega e to the power j omega t d omega, isn't it? Here I am changing omega to minus omega. Okay. Now this is x star t. Now tell me what is the Fourier transform of x star t? What is the meaning of this integral on the right hand side? Is it the inverse Fourier transform of, does it mean that inverse Fourier transform of x star minus j omega, that is x star t? Is it the meaning?
Yes, sir.
So what is this? Is it x star minus j omega? X star minus j omega?
Yes, sir.
So it is same. If you remember the property of Fourier series also, like if xt is ak, then x star t is what? A star minus k, isn't it? That is the property in the case of Fourier series. Here also it is similar. X star t, it is x star minus j omega. Now if you consider a real valued signal, if you consider a real valued signal, then what is a real valued signal? Xt is, this is a real valued signal. So if these two signals are equal in the time domain, in the frequency domain also, we can write x of j omega is equal to x star minus j omega. Okay. Now, can you tell me some property of the magnitude and phase of a real valued function? So if you consider this expression, can we write this as x star j omega x of minus j omega? Can we write like this? You either change omega to minus omega or take the complex conjugate on both sides, you will get this expression. Now, if you take the magnitude on both sides, what is the magnitude on the left-hand side? Magnitude of x star j omega. Is it same as x of j omega?
Yes.
Because if you consider a complex number a plus jb, in the polar form, we can write it as z is r e to the power j theta, isn't it? This must be the standard notation you have studied. Z is r e to the power j theta. This is in the polar form. What about the complex conjugate of that? What about the magnitude? Will it remain the same? Is it this?
Yes, sir.
R e to the power minus j theta. So can we write this if we take the magnitude on both sides? What does it mean? X of j omega is this. What is that? What does it mean?
Sorry, even function.
It is the magnitude spectrum. Magnitude. This is the magnitude spectrum. Magnitude spectrum. What type of function is that? Is an even function of omega. Okay. That is an important property. The magnitude spectrum of a real valued signal. Magnitude spectrum of a real valued signal is an even function of omega. Can you tell me about the phase spectrum of a real valued signal? This is the relation for a real valued signal. Can you tell me what is the relation between the phase spectrum? What is the phase of this x star j omega? You can get it from here. Can we say that phase of x star j omega, how is it related with the phase of x of j omega?
Minus of phase of x of j omega.
It is minus of x of phase angle of x of j omega, isn't it? It is from evident from here, because here the phase is minus theta. Here for z, if it is theta, z star, the phase is minus theta. Okay, so now tell me what is the relation? Can we write from this x of phase angle of x of minus j omega, is it minus phase angle of x of j omega? Is it that?
It is odd function.
You can get from here. Okay, so this implies that phase spectrum is phase spectrum of a real valued function is always an odd function of omega. Okay, so this is an important property for a real valued signal. Its magnitude spectrum is an even function of omega, and its phase spectrum is an odd function of omega. Let us consider an example. We discussed this earlier, e to the power minus at ut. Is it a real valued signal? E to the power minus at ut, it is a real valued signal. What is the Fourier transform of this? 1 upon a plus j omega. And what about the magnitude and phase spectrum of this? What is magnitude spectrum? Is it 1 upon root of a square plus omega square? And phase angle is tan inverse omega by a. It is not tan inverse minus tan inverse omega by a. We derived this in the previous class. Okay, and we can sketch this. The magnitude spectrum is something like this. It is just approximate shape. It is x of j omega. It is an even function. It is symmetric about the y-axis, and the phase spectrum is, I think it is minus pi by 2, and this is pi by 2. It's you can see that its phase spectrum is an this is phase angle of x j omega. It is an odd function of omega because it is antisymmetric about the y-axis. Okay, and this is true for any real valued signal. Okay, any question regarding this property? And there are other properties like this property. If xt is x of j omega, x of minus t is x of minus j omega. This is also straight. Proof is straightforward. You just change the variable, you will straight away get this property. And again, it is similar to the property of Fourier series. Like if you flip the signal, the Fourier series coefficients are also flipped. Here, if you flip the signal, its spectrum is also flipped. And you can combine these two properties like conjugation and this property, flipping property. I am leaving this as an exercise. If xt is real and even, if xt is a real and even function, that implies that x of j omega is real and even. And if xt is real and odd, x of j omega is purely imaginary and odd. Okay, you can easily prove this. Consider two signals x1t. Let's say the Fourier transform Fourier transform of x1t is x1 j omega, and x2t, its Fourier transform is x2 j omega. Okay, two signals x1t and x2t. Now, if you convolve these two signals, what is the Fourier transform of the convolution? The convolution of x1t and x2t. Okay. How to find the Fourier transform of this? What is the expression for that? Is it integral minus, you are given any signal? It's the Fourier integral is x1t convolution x2t. This is a signal, time domain signal, and you multiply it with e to the power minus j omega t and then integrate over t. That is how we find the Fourier transform of a signal. Can we simplify this? No, not simplifying. If we expand this convolution operation, can we write this as integral minus infinity to infinity? Now I am expanding this convolution. Integration from minus infinity to infinity, x1 tau, x2 t minus tau, e to the power minus j omega t dt. Okay, I'm just expanding that. Now, if I'm now I'm what I'm doing here is I'm
Now
expanding. Oh, sorry, there is a integration with respect to tau. The tau is there. Okay, so this is this convolution. This is the convolution integral. Okay, I'm expanding this term. Now, if we interchange the order of integration, can we write it as minus infinity to infinity x1 tau integral minus infinity to infinity x2 t minus tau e to the power minus j omega t dt, and then integrate with respect to tau. I'm changing the order of integration. Can we simplify this? What about the integration in this bracket? Okay, I'm putting t minus tau is, I'm changing the variable. I'm putting t minus tau is u. So we'll get this integration as integral minus infinity to infinity x1 tau integral minus infinity to infinity x2 u e to the power minus j changing the variable. T minus tau is u. Is it okay? Is this correct?
yes, sir.
Okay, now can we simplify this? Here we can, this is integration with respect to u. So we can write it as integration minus infinity to infinity x1 tau. I am taking this term outside e to the power minus j omega tau. Then the integration is minus infinity to infinity xt x2 u e to the power minus j omega u du. Okay, and then integration with respect to tau. Now, what about this integral? Can you tell me what is this integral?
Fourier transform of
X
X to j omega.
It is the Fourier transform of x to u, isn't it? So can we write this as, because it is a function of omega, we can take it outside the integral. It is x to j omega, that is this term, this integral, into integral minus infinity to infinity x1 tau e to the power minus j omega tau d tau. Okay. Now what about this?
x1 j omega.
It is x1 j omega. So we can write it as x1 j omega into x2 j omega. Okay. So that is the multiplication property. That property states that if x1t Fourier transform is x1 j omega and x2t Fourier transform, okay, this is x2 j omega, then if you convolve two signals x2t, then it is multiplication in the Fourier domain. Okay. Convolution in the time domain, it is multiplication in the frequency domain. We will be discussing many applications of this property in later classes. Okay. So this is very important property. You have to remember this. And there is a dual of this property. That property is, I am just stating that without proof. If you multiply the signals in this frequency time domain, here we are convolving two signals in the time domain. Now, if we multiply two signals in the time domain, it is convolution in the frequency domain. Okay, that is the there is a scaling factor 2 pi. 2 pi into convolution of these two. So it is easy to remember. Convolution in one domain, multiplication in the other domain. Okay, except these scaling factors. What is the Fourier transform? If the Fourier transform of xt is x of j omega, then what is the Fourier transform of x of at? Whether it is related with x of j omega or not. What is the Fourier transform of this? Isn't it? That is the Fourier transform. Here the function is x of at, and it's for a, this is how we find the Fourier transform using this Fourier integral. And we can, if I am substituting the variable, let's say tau is equal to at, then what about this integral? Is it this?
Yes, sir.
Or something, remember, something missing there?
1 by a.
It is 1 by a. Is it 1 by a or is it always 1 by a?
1 by mod a.
It is 1 by mod a. The reason is that if a is greater than 0, it is 1 by a. And if it is a is less than 0, it is minus 1 by a. Isn't it? Is it? Because the limits will change. So, is this? Because if for a less than 0 minus 1 by a, we can write it as mod a. So this is the time scaling property. So sorry, we have not completed it. Now can you tell me how is this related with x of j omega? You compare these two and tell me what is the Fourier transform, how are they related? Can we write this integral in terms of x of j omega?
1 by mod A x of j omega by A.
That is the scaling property. This is called the time scaling property of Fourier transform. And we have already seen some examples of this. First, let us discuss what is the significance of this value of A. If A is greater than 1, is it compression or expansion in the time domain? Let's say A is 2. It is expansion or compression?
Compression.
It is compression by a factor of 2, isn't it? If A is 2, then it is compression by a factor of 2. Now, what will happen if there is a compression by a factor of 2 in the time domain? What is its effect in the frequency domain? It is
Expansion by a
it is
Expansion.
expansion by a factor of 2, isn't it? So there is an inverse relation. If we compress in the time domain, it is expansion in the frequency domain. Okay, and we have seen this example also. If we consider a rectangular pulse 0 t1 minus t1, and this one is a sinc function, its Fourier transform is a sinc function, and which are these zero crossing points? Its expression is, if you don't remember it, the expression is 2t1 sinc omega t1 by pi. Okay, so where will this be? No, 0. This, for which values of omega this would be 0? This point is what? Is it pi by t1? The first zero crossing point, then it is 2 pi by t1, integer multiples of pi by t1. So you can see that if we compress this, if we reduce the value of t1, there is an inverse relation. Okay, its value in the frequency domain, there is an expansion. Okay, so that is the time domain, time scaling property.